Hi, in this video we'll be talking about an application. So let's get into the problem. You are given a fixed array A of size n and a fixed integer k. You need to answer q queries of the form $LR, and for LR given, you need to find the value of the expression modulo 10 to the power 9 plus 7. A of L plus A of L plus 1 multiplied by k plus A of L plus 2 multiplied by k square, and so on, right? So as you can see in this, you have first one multiplied by 1, second one multiplied by k, then k square, then k cube, so on, and that you multiply these terms with the subarray L to R, and you need to find this value modulo mod. Okay. So whatever expression operations that we'll be doing modulo this value. Okay, so let's quickly have a look at an example. So let's say k is equal to 2 and you need to find the answer for 2 to 4. Okay, so 2 to 4 is this range, right? 2 to 4 is this range. Now to evaluate the value, we can just put in the values from this. So this will be 9 plus 4 times 2 plus 1 times 2 square, right? And this will be 9 plus 8 plus 4, and this is 13 plus 8, 21. Right? So this is the value of an example query. You need to answer q such queries. So now if you loop from L to R for every query, you can find out this value pretty easily. You can maintain a variable with the corresponding power of k. Whenever you come to a term, multiply the corresponding power of k, add it to the answer, increase the power of k, and move to the next term. If you do that from L to R, you can answer each of the query in order n, right? For each of the query, you will need order n on the worst case, because the whole subarray might be there in the query. And across all q queries, it will take you order q into n for the whole problem. But of course, we want to do better than this. So how do we do that? So let's look at the expression carefully. So first of all, we'll be writing this in a generalized form of summation notation. So let's say we try to write it as I equal to L to R A of I. And what do we multiply with A of I? First one gets multiplied with k to the power 0, k to the power 1, k to the power 2, so on, right? So it gets multiplied with k to the power I minus L, right? Because when you put L over here, this gets to 0 and this gets to 1, so that's there. And at the end, if you put R is also correct, right? So if these two terms match, most probably the expression is correct. And this is the expression that you need to evaluate for the queries. Now, if we look closely into the term over here inside the summation, we can notice that we can somehow decompose this to extract out the query part from it. So in this, only thing that depends on the query is this L, right? So what we can do is that we can convert this into summation, and from now on every summation means from L to R A of I times k to the power I multiplied by k to the power Lth inverse, right? K to the power L inverse. So this is what this means, and now this is constant from I equal to L to R, right? This is constant, so we can take that out of the summation and we get k to the power minus L summation AI times k to the power I, right? Now this k over here is given fixed, right? This observation is important, because now what we can do is that we know all of these things are fixed, right? A of I, k, I, all of these things are fixed, and it only changes from I equal to L to R. So what we can do is that we can kind of rename this into a bi variable, which is equal to A of I multiplied by k to the power I. Okay, so we rename into just a new variable. So now this bi variable can be found using just looping over from I equal to 0 to n minus 1 in the array A and multiplying with corresponding power of k, right? So this is a static array if A is a static array. So we can easily calculate this array B. Now this question just boils down to finding k to the power minus L summation of B of I from I equal to L to R. So notice how we converted it into another static array, and then we just say that okay, this is the sum of that static array in that range, right? And now we know that this sum we can easily calculate using prefix sums, because this is just a static array and it's sum from L to R. So finding this using prefix sum would take us just order 1, right? We can find this summation of L to R in order 1, and once we get this value, we can multiply it with k to the power minus L separately to get the answer for the query, right? So for the answer of the query, you can just multiply it with k to the power L minus 1 after finding out this query from the prefix sum. So what we are doing is that we have the array A, we just transform it into a B array using this multiplication A of I times k to the power I, right? So for every index, k is fixed, I is fixed, A of I is fixed, right? So all of these values can be easily created by a loop from 0 to n minus 1, and once we have this B array, we can build a prefix sum over this. So this is just building prefix sum, okay? And once we have this prefix sum, every query will need this range sum of B, right? So that we can get from this prefix sum in order 1, right? And once this prefix sum gives us order 1, we just plug in that value from into this expression over here, okay? Now if we look at the time complexity, there are q queries and each of them needs this summation, right? And each of these summation can be calculated in order 1, because we are doing linear computation over here. We can maintain k to the power I in a looping fashion. Whenever we loop, we keep increasing k of I, and we can just multiply and get the bi value in order n, okay? And then if we build a prefix sum, we can get the sums in order 1. So this also takes order, this also takes order n, this also takes order n, and then for every query it will take order 1 to get this summation. But we have this k to the power minus L over here, right? This k to the power minus L. So if we want to calculate this, we can do it using binary exponentiation. We can calculate k to the power L and invert that, and that would take us order log n. So if we do it by binary exponentiation, we would need order log n. To even minimize on that, what we can do is that we can pre-compute all values of k inverses. So first of all, what you can do is that you can calculate the value of k inverse, okay? That takes you order log n, right? And then build an array of inverse powers of k. So what you do is that you build an array of k inverse where you save the k inverse of 1 is equal to this value, okay? Whatever value you get, you put in there, okay? And then k inverse of 2 is equal to k inverse of 1 multiplied by this x, whatever you value over here. Let's call this x. You just multiply this value over here. So we know that k to the power minus m is equal to k to the power minus m minus 1 multiplied by k to the power minus 1, right? And this k to the power minus 1 is x, so you know that. And this you can calculate from the previous calculated value. So you can take that in order 1 and take this in order 1, and you can multiply and take modulo and just keep the value of k inverses in an array. So computing this previously before you start any computation will take you an order n, right? This order log n is just one time cost. So order log n plus order n. So if you pay this order log n plus order n cost, you will need order log n plus n cost to build this k inverse array. But then every query will have k to the power minus L, and this L can only be in the range of 0 to n minus 1, right? The L has to be inside the array. So there are only n number of different values that you need to store. So all of them are readily available in this array. So you can find this value in order 1, right? you can take this value in order 1 from the inverse array. You can take this from this inverse k inverse array that you created. So with this pre-computation as well, you can get the whole query part in order 1. So we can solve this problem in order n pre-computation, in fact n plus log n, but obviously n is dominating, so that we don't mention log n in the expression. And for each query you now need order 1, right? So that's all for this video. Thank you.